So we know how this works out. We get for the first term sum over m dm dot psi L dot m psi m plus sum over m dm psi L dot k psi m equals 0. All right. Now this we know from the orthonormality condition is delta Lm. Okay? And this we know also from the fact that we have the generalized eigenvalue problem at hand. This turns out to be lambda m delta Lm. Okay? And then when we account for the fact that there is a sum over m in each case, the Kronecker delta does its job and leaves us with the following. Okay? What it leaves us with is for the first term, we get dl dot plus. From the second term, we will get dl, well, let me put the lambda in front. We get lambda L dl equals 0. Okay? Right, and this came about just by applying the properties of the Kronecker delta and using that sum, right, over m. Okay? Now, we did this for an arbitrary mode or an arbitrary eigenvector psi L. Okay? So this holds for all, well, this holds for all L actually. For all L equals 1 to NDF. Okay? All right. This is what we will call our single degree of freedom modal equation. Okay? Reduces to a really simple form. All right? Okay. So we have this, and what I'm going to do is very systematically do essentially the same thing for our time-discrete homogeneous ODE. Okay? Okay, let's first write out that ODE, right? We'd agreed that as far as analysis was concerned, we were going to work with it in the following form. Okay, this is the form that we're going to work with. I'm going to rewrite this by just expanding out dn plus alpha and also multiplying through by delta t. Okay, so in one step, I'm going to say that I have m dn plus 1 minus dn plus delta t k times alpha d at n plus 1 plus 1 minus alpha d at n equals 0. Okay, just multiplying through by delta t here and expanding out dn plus alpha. Okay, so that is right. Okay, and let's go ahead from here and essentially introduce modal decompositions of dn plus 1 and dn. Okay. Right, so the modal decompositions we are going to apply here are d at n plus 1 equals sum over m, the modal coefficient m evaluated at n plus 1. Okay, this is the modal coefficient, the mth modal coefficient of the d vector at n plus 1, right, the time t n plus 1, right, psi m. Okay, I don't really need to write the same thing for n because it's just replacing n plus 1 with n. Okay, right, so likewise for dn. Okay, we carry out those modal decompositions and then we also substitute them back. All right, so now when we make the, we go ahead and plug them into the last equation from the previous slide. We have m. Okay, let me do two things in one step here again, if you don't mind. I am going to write, I'm going to combine the matrices multiplying dn plus 1 and the matrices multiplying dn, okay, in a single step. Okay, so for dn plus 1 I have m plus alpha delta t k, right, multiplying dn plus 1, but dn plus 1 I'm going to write using this modal decomposition. Sum over m d, right, that coefficient, the dm coefficient at n plus 1, right, psi m, okay, and the things multiplying dn I'm going to write as follows. Okay, I'm going to write this as minus m minus 1 minus alpha delta t k, and hopefully I got everything I need to. Yes, I did. Dn, but dn again I'm going to write using the modal decomposition. Right, all of this equals 0. Okay, so I've taken two steps here relative to the last equation that I wrote on the previous slide. I've combined the matrices that multiply the dn plus 1 and dn, okay, the dn plus 1 and dn vectors, as well as using the modal decomposition for dn plus 1 and dn, right. So this is, and this is that modal decomposition. Okay, that's what we have. Right, and you know what I'm going to do next, right? What I need to do is go from here. This is a vector equation, of course. Go from here to a scalar equation for a single degree of freedom, and we're going to do that by simply dotting this on the left, well, dotting this with psi l, right? So I'm going to do psi l dotted with all this, okay, and likewise here I have psi l dotting everything. Okay? And then using linearity and so on, what we get here is the following. We get sum over m d m n plus 1 multiplying psi l dot m psi m, okay, right, plus alpha delta t psi l dot k psi m, okay. All right, all of this minus sum over m d n m, we open parentheses here, psi l dot m psi n, sorry, m psi m minus 1 minus alpha delta t psi l dot k psi m. Okay, all of this equals now, what is it? Vector or scalar? 0. Scalar 0. Okay, and then everything works out just as expected. This thing gives us a delta Lm. From here we get a lambda m delta Lm. Okay, here again we get delta Lm, and from here we get lambda m delta Lm. Okay, all from orthonormality and from the eigenvalue problem. Right, and then we account for the fact that we do indeed have a sum over m, and what that lets us say then is that because of the action of the Kronecker delta, we are left here with essentially the action, what the Kronecker delta does because of the sum over m is that it effectively converts that index m into L. Okay, so we have delta L n plus 1, okay, from the first term here, okay, we get 1 plus alpha delta t here again because of the Kronecker delta acting on multiplying the lambda m, we are left with alpha delta t lambda L, okay, minus d at n for the nth mode times 1 minus alpha delta t lambda L. Again, that lambda L comes from here and the action of the Kronecker delta. Right, all of this equals 0. Okay, this is our equivalent for the time discretized ODE of the single degree of freedom modal equation for the time exact ODE. Okay, so this is the single degree of freedom modal equation, right, for the time discrete problem. All right. Okay, it is to be compared with the single degree of freedom modal equation that we obtained for the time exact problem. Okay. All right. This is actually a great place to stop. When we return, we are going to analyze the two single degree of freedom modal equations. Oh, just one more thing. I should mention that this holds for all L equals 1 to NDF. Okay. All right.